Namaste. I am Mrs. Arumugalakshmi. Today we are going to discuss the problems in Lesson 5, Motion of System of Particles and Rigid Bodies of Class 11 Physics. First problem. From a uniform disk of radius r, a small disk of radius r by 2 is cut and removed as shown in the diagram. Find the center of mass of the remaining portion of the disk. So as shown in the diagram, we are considering the mass of the full disk as capital M. So the center of mass will be lying in the geometric center of the disk, that we already know. So the center will be lying at this point. If you note my pointer, you can find that the center of mass will be lying here. So now here a portion of mass is cut from this disk. That is a portion of r by 2, the one which is shaded in dark blue is cut. So the remaining portion is r by 2 is cut. So the remaining portion is the light blue colored portion. So for this light blue colored portion, the center of mass will lie at a distance of x. If you see my pointer, you can easily identify. Let x be the center of mass of the remaining portion which has been cut from the total mass. So now we can apply our principle of moments. According to the principle of moments, mass into perpendicular distance. Here the first mass is, the total mass is m, that is total mass of the disk is capital M. Among that, one small portion is cut off, which is small m is cut off. So the remaining portion will be m minus m, and the distance between them is x. So m minus m into x is equal to the mass which is cut is small m, and where here the center of mass is at a distance r by 2. So which is equal to m into r by 2. So here we need to find the center of mass of the remaining portion, that is x value we have to find. So from this equation, if you reverse x, you get x is equal to m the whole divided by m minus small m into r by 2. So we need to substitute all these values in this equation x to find the value of x. So for that we assume the surface mass density as sigma. Sigma is the surface mass density, which means that on the particular surface how much mass is distributed. Here sigma is equal to the total surface seems to be a circle. So the total surface area is pi r squared. The total mass distributed is capital M. Hence sigma is equal to m by pi r squared. Now from this we will find the mass of the small disk, which is small m. So m can be written as surface mass density into surface area. So m is equal to surface mass density, we know the symbol as sigma, into surface area, which is here for the portion which is cut by r by 2, the surface area will be pi r square. Instead of r, we should have r by 2. So the area is pi into r by 2 the whole square. So now substitute the sigma value. Sigma already we have found the expression as m by pi r square. Substituting in this equation and simplifying, you get the mass of small m as capital M by 4. So now this value of small m we have to substitute in the expression for x we saw in the previous slide. So substituting that, we get x is equal to m by 4 divided by m minus m by 4 into r by 2. M minus n by 4 we know the value as 3m by 4. So simplifying this, we get the value of x as r by 6. The next question, the position vectors of 2 point masses 10 kg and 5 kg are minus 3i cap plus 2j cap plus 4k cap into m and 3i cap plus 6j cap plus 5k cap m respectively. Locate the position of the center of mass. So as shown in the diagram, two masses are lying and the center of mass will be lying in the center between these 2 points. So to find that, we are using the center of mass formula, which is R vector is equal to m1 r1 plus m2 r2 divided by m1 plus m2. So substituting the m1 value, r1 value, m2 value and r2 value, we get 10 into minus 3 I cap plus 2 j cap plus 4 k cap plus 5 into 3 I cap plus 6 j cap plus 5 k cap. So multiplying 10 inside the first bracket, we get minus 3 I cap plus 20 j cap plus 40 k cap plus, similarly this side you have to multiply 5 inside. So you will have 15 I cap plus 30 j cap plus 25 k cap divided by 15. So further simplifying this, we get the answer of R vector as minus I cap plus 10 divided by 3 j cap plus 13 divided by 3 k cap meter. This is the value of center of mass. The next problem. Locate the center of mass of a uniform rod of mass m and length L. So here we are considering a rod whose mass is m and the length is L. So for this we need to find the center of mass where it will be lying. We know that center of mass is given by the formula integral x dm divided by integral dm. So now we will find the center of mass. So first we are taking the whole rod of mass m and length L. So first for a small portion we will be finding, then for the total portion we will be integrating within the limits and we will find. So here we are introducing a new concept called lambda, which is the linear mass density. Linear mass density means in the particular length how much mass is distributed. So here the length is L, the mass distributed is m, so lambda will be m by L. Now the mass of the small element dm will be lambda into dx. So lambda value is given by m by L. So m by L into dx is the value of dm. Now we know the formula of xcm. Here we are going to substitute the dm value. So xcm is equal to integral 0 to L x into, instead of dm I am going to substitute m by L into dx, divided by integration of dm will be the total mass m. Now taking the common terms outside, m in the numerator and m in the denominator get cancelled. So we have integral 0 to L x dx. Integration of x, we know that it is x squared by 2. Applying the limits, we have 1 by L into L squared by 2. Cancelling the L on numerator and denominator, we have xcm as L by 2. The next problem. A man of mass 50 kg is standing at one end of the boat of mass 300 kg floating on still water. He walks towards the other end of the boat with a constant velocity of 2 meters per second with respect to a stationary observer on the land. What will be the velocity of the boat? First, with respect to the stationary observer on the land. Next, with respect to the man who is walking on the boat. So mass of the man is given as 50 kg, mass of the boat is given as 300 kg. So first let us find with respect to a stationary observer. So with respect to stationary observer, the man is moving with the velocity 2 meters per second and the boat moves with the velocity v2, which we have to find. So first let us find the velocity of boat with respect to a stationary observer. Here there is no external force acting on the system. The man and the boat they are moving only due to the friction, and friction is considered to be an internal force in the boat-man system. Hence the center of mass velocity will be equal to 0. For internal force it will be equal to 0. So here you can see the man moving towards the other end of the boat. Now we will find what happens to the velocity. So we know that center of mass is equal to 0. So we equate the formula for center of mass is equal to 0. Hence 0 is equal to summation m1 v1 divided by summation m1. Summation m1 v1, if you expand, you get m1 v1 plus m2 v2 divided by m1 plus m2. Since the center of mass is equal to 0, the term in the LHS will be 0. So taking the denominator there, we have that term also 0. Hence, we get the equation minus m1 v1 is equal to m2 v2. We need to find v2. So, v2 is equal to m1 by m2 into v1. Now, substituting the m1, m2, v1 value from the given data, we have v2 is equal to minus 0.33 meter per second. Now we have to determine the velocity of the boat with respect to the walking man. Here, the relative velocity is given by v21, which is given by v2 minus v1. v2 now only we found that minus 0.33, v1 is 2. So, minus 0.33 minus 2 will give you the answer of v21, which is equal to minus 2.33 meter per second. Next problem. A projectile of mass 5 kg in its course of motion explodes on its own into two fragments. One fragment of mass 3 kg falls at 3/4 of the range r of the projectile. Where will the other fragment fall? So first we are going to use the principle of moments formula here, which is m1 x1 is equal to m2 x2. Here m1 is the 3 kg mass and m2 is the 2 kg. And here x1 is equal to 1 by 4r, that is 1/4 of the range the object is displaced. So we need to find the value of x2 where the second object falls, that we need to find. That you can see in the animation given below. Here x2 is the distance d which we need to find. That is the distance at which the second object is lying on the floor, that we need to find. So substituting this m1, m2, x1, x2 value in the principle of moments, we have 3 into 1 by 4r is equal to 2r. Simplifying, we get d is equal to 3 by 8r. So the distance of point of launching of the 2 kg mass is r by d. Now, the distance between the point of launching and the point of position of 2 kg mass is r plus d. So, r we know. Now only we found the value of d as 3 by 8 r. So, adding them, taking LCM and adding them, we have 11 by 8 r. 11 by 8 value is 1.375 r. So, the other fragment will fall at a distance 1.375 r from the point of launching. Here r refers to the range of the projectile. The next problem, if the force applied is perpendicular to the handle of the spanner as shown in the diagram, first find the torque exerted by the force about the center of the nut, the direction of the torque, type of rotation caused by the torque about the nut. Here the arm length is given by r is equal to 15 centimeter. Converting this into meter, we have 15 into 10 power minus 2 meter. The force is given as 2.5 Newton. The angle between r and f, when you see the diagram itself, you can know that the angle between them is 90. We know the formula of torque as tau is equal to rf sin theta. Substituting r value, f value, sin theta value, we get 15 into 10 power minus 2 into 2.5 into sin 90, which is equal to 1. Hence, tau value is given as 37.5 into 10 power minus 2 Newton meter. So, to find the direction of torque, we apply the right hand rule. So, according to this rule, the direction of torque is out of the page and the type of rotation is anti-clockwise. If you see the diagram itself, you can understand the type of rotation is anti-clockwise. Next problem. A force of 4 I cap minus 3 j cap plus 5 k cap Newton is applied at a point whose position vector is 7 I cap plus 4 j cap minus 2 k cap. Find the torque of the force about the origin. So R vector is given, F vector is given. So we can easily find the torque value as tau is equal to R cross F. Here we have to use the vector cross product. We know to find the vector cross product. We have to have the determinant formula I, J and K cap, and you have to write the components below and we have to do the multiplication. This method already we have seen in the unit 2. So tau is equal to I into 20 minus 6 minus j into 35 plus 8 plus k into minus 21 minus 16. Simplifying, we get the value of torque as 14 I cap minus 43 j cap minus 37 k cap Newton meter. The next problem, a crane has an arm length of 20 meter inclined at 30 degree with the vertical. It carries a container of mass 210 suspended from the top end of the arm. Find the torque produced by the gravitational force on the container about the point where the arm is fixed to the crane. Here the value of 110 is given as 1000 kg. Neglect the weight of the arm and G value is given as 10 meter per second square. We need to find the torque. So tau is equal to R cross F sin theta. So theta value, if you see the diagram, follow my pointer, you can easily find the angle theta. Theta is the angle between the wire in which the mass is hung and the arm of the crane. So if you see that this total angle is 180 and this angle is 30. See the diagram? Here this angle is 30. So alternate angle, this angle also will be 30. So total angle is 180. So this angle is 30. So 180 minus 30 will give you this angle which is 150. So here the theta value is 150 which can be written as 90 plus 60. So R value is 20 meter and F value we use the formula F is equal to mg. M is 2 ton. So 2 into 10 power 3 into G value is again 10 meter per second square. So multiplying we have 4 lakh into sine 90 plus 60. Sine 90 plus 60 is nothing but cos theta. So 4 lakh into cos 60 which is nothing but 1 by 2. So the answer is 2 lakh Newton meter. This can also be written as 2 into 10 power 5 Newton meter. The next problem, three mutually perpendicular beams AB, OC, GH are fixed to form a structure which is fixed to the ground firmly as shown in the figure. One string is tied to the point C and it's free. The end D is pulled with the force F. Find the magnitude and the direction of the torque produced by the force, first about the point D, C, O and B. Next about the axis CD, OC, AB and GH. So first let us find about the point D. About the point D, the torque is equal to 0. Why it is 0? Tau is equal to R cross F. If the angle between the R vector and F vector is 0, the torque will also be 0. See here in this diagram, F is acting downwards and the displacement is also downwards. So the angle between them is 0. Hence the torque about the point D is 0. Similarly, the torque about the point C is also 0. Here also the position vector and the force are lying along the same axis. So here also the torque is 0. Next about the point O. If you see the point O, it is here. So here the torque is given by the perpendicular distance, force into perpendicular distance. Force is this F and the perpendicular distance is OC. So F into OC will give you the torque and it is along GF. Torque about the point B. the point B is lying here. So here also the torque is given by the perpendicular distance, which is BD. B into D, this is the perpendicular distance, and the force is given by F. So F into BD will give you the torque about the point B. Next, we need to find the torque about the axis CD. The axis CD is again lying along the same line where the force is acting. Hence, the torque about this axis is 0. Next, the torque acting along the axis OC. This is also 0 because the force F is intersecting with the line OC. Hence, here it is also 0. Next, about AB. AB is again parallel to the line CD. Hence, here also it is 0. Then along the axis GH. Here it is not 0. It is inclined at an angle theta. So, force F into the perpendicular distance OC will give you the torque along GH. Next problem. A particle of mass m is moving with the constant velocity v, and it is moving along the straight line which is given in the diagram here. Show that its angular momentum about any point remains constant throughout the motion. So we will consider an object of mass m which is moving with the constant velocity. Since it is moving with the constant velocity, it will have a momentum which will also be the linear momentum, which is given by P is equal to mv, which is also will be in the same direction of the velocity. Now we will fix the origin at O. If you see the diagram, the origin is at O and the perpendicular distance from the origin to the path of the mass is small d. So at any particular point, we can draw the position vector r as OQ. OQ is the r vector, which is the position vector of the object which is moving. So the magnitude of the angular momentum is given by L is equal to OQP sin theta. That is, L is equal to RP sin theta. We have here, instead of R, we have the length OQ. So OQ into P sin theta, which is equal to OQ into P value, we know that it is mv. So it is mv sin theta. So take mv outside and take OQ inside. We have mv into OQ sin theta. The term OQ sin theta is nothing but the perpendicular distance between the origin and the line along which the mass is moving. Hence, you can replace that OQ sin theta as the distance d. So, L will be equal to mvd. This is the expression for angular momentum. Here, if you see the equation for L, mass, velocity and distance. L is a product of mass, velocity and distance. And mass will be a constant, as you know. The distance d is also a constant and the velocity is also constant as per the question. So in the question it is given that it is moving in the constant velocity. So v value is also constant. Hence L, which is a product of m, v and d. M, v, d all are constant. So the product of all three will again be a constant. Hence the angular momentum is also a constant. The next problem. Arun and Babu carry a wooden log of mass 28 kg and length 10 meter, which has almost uniform thickness. They hold it by 1 meter and 2 meter from the ends respectively. Who will bear more weight of the log? So we know that for translational equilibrium, the total force acting on the log must be equal to 0. If you draw the free body diagram, the force, if you find my diagram, you can see the force is acting along mg. The force exerted by Arun is acting along RA. The force exerted by Babu is acting along RB. Hence, if you write the equation, you have RA plus mg plus RB is equal to 0. RA and RB are positive. Mg is negative since it is acting in the downward direction. Hence, you take this minus mg to the equation other side. You have Ra plus Rb is equal to mg. This is the equation for translational equilibrium. For rotational equilibrium, we know the condition as torque is equal to 0. Hence, the torque is given by force into perpendicular distance. So, here it is O into Ra plus minus 4 mg plus 7 into Rb is equal to 0. Here we have torque is given by force into perpendicular distance. Here the point of reference is taken to be A. So, first force Ra is lying on A. So, the perpendicular distance from A to A is 0. So, you have got the torque as 0 into Ra plus minus 4 mg. Mg, if you follow my pointer, mg is at a distance 4 meter. So the torque is 4 into mg. Since it is acting minus direction, you have got minus mg plus 7. See, the point B is at a distance of 4 meter plus 3 meters. So it is 7 into Rb is equal to 0. So first term will get cancelled. So you have got 7 Rb is equal to 4 mg. So Rb is equal to 4 by 7 into mg. Substituting m value and g value, we get Rb value as 160 Newton. Now we have to substitute this Rb value in the Ra value, that is Ra is equal to mg minus Rb. In this equation you have to substitute for Ra. We have Ra is equal to 28 into 10 minus 160, which is equal to 280 minus 160, which is equal to 120 Newton. So if you find the value, Rb is greater than Ra. So Babu will bear more weight than the Arun. A cyclist, while negotiating a circular path with speed 20 meters per second, is found to bend at an angle 30 degrees with the vertical, which you can see in the animation how the cyclist is bending when he is going in a circular path. What is the radius of the circular path? So, speed of the cyclist is 20 meters per second. Angle of bending is given as 30 degree. We know the equation for angle of bending, tan theta is equal to v square by rg. So, here we need to find the r value. So, rewriting this equation for r, we get r is equal to v square by tan theta into g. Substituting the v value, theta value, g value, we get r is equal to 20 square divided by tan 30 into 10. So simplifying this, you get the answer as 400 divided by 1 by root 3 into x. So root 3 will go to the numerator. So we have 40 root 3. Root 3 value is 1.732. So multiplying that with 40, you have 69.28 meter. The radius value is 69.28 meter. The next problem, find the moment of inertia of a uniform rod about an axis which is perpendicular to the rod and touches any one end of the rod. We know the moment of inertia value as I is equal to m by L integral 0 to L x squared d squared. We would have seen in the theory part this equation. So substituting in this equation 0 to L we have to integrate. So you have m by L integration of x squared is x cube by 3. Substituting the limit we have m by L into L cube by 3. So simplifying, cancelling this L in the numerator, L cube in the numerator and L in the denominator, we have 1 by 3 m L squared. Find the radius of gyration of a disk of mass m and the radius r rotating about an axis passing through the center of mass and perpendicular to the plane of the disk. You can see the disk which is flying in the animation. The moment of inertia is given by the formula I is equal to half m r square. In terms of radius of gyration, we know the value of I as m k square. So in these two equations, moment of inertia is the same. So equating the RHS, we have half mr squared is equal to k squared. So cancelling m on both the sides, we have k squared is equal to 1 by 2 r squared. Hence k will be equal to square root of 1 by 2 r squared. So square root of 1 by 2 is 2. Square root of r squared is r. So 1 by root 2 value is 1.414. So k is equal to 1 by 1.414 into r, whose value is 0.707 r. This is the value of k. Next problem. Find the moment of inertia of a disk of mass 3 kg and radius 50 cm about the following axis. First one, axis passing through the center and perpendicular to the plane of the disk. Second one, axis touching the edge and perpendicular to the plane of the disk. And the third one, axis passing through the center and lying on the plane of the disk. So first one, we will find the moment of inertia about the axis passing through the center and perpendicular to the plane of the disk. So this is given by I is equal to half m r squared. So substituting m value and r value from the given data, we have 0.5 into 3 into 0.5 into 0.5, which is equal to 0.375 kilogram meter square. Next, we need to find the moment of inertia about an axis which is touching and perpendicular to the plane of the disk. So here we use our parallel axis theorem, which is I is equal to IC plus MD square. IC value is nothing but half mr square. D value is nothing but r. Hence, I is equal to half mr squared plus mr square. Instead of d, we have got r, which is equal to half plus 1, which is equal to 3 by 2 mr square. So 3 by 2 into m value is 3, r value is 0.5 the whole square. Multiplying and simplifying, you have I is equal to 1.125 kilogram meter square. Next, we need to find the moment of inertia about an axis passing through the center and lying on the plane of the disk. That is, Iz is equal to Ix plus Iy. Here, Ix and Iy will be equal to I, and Iz is equal to half mr squared. When you substitute Iz value for Ix and Iy as given as I, if you substitute in Iz equation, you have Iz is equal to 2y. Hence, I will be equal to Iz by 2. So, Iz value is found to be half mr squared. Substituting in this equation, we have I is equal to half into half mr squared, which will be equal to 1 by 4 mr squared. Substituting m value, r value, we have I is equal to 1 by 4 into 3 into 0.5 the whole square. Multiplying and simplifying, we have I is equal to 0.1875 kilogram meter square. The next problem. Find the moment of inertia about the geometric center of the given structure made up of one thin rod connecting two similar solid spheres. So if you take this figure, if you see the diagram, this figure is made up of three structures, two spheres and one thin rod. So the moment of inertia of the rod is 1 by 12 mr square, and for the sphere it will be 2 by 5 mr square. So substituting all these values, we need to find the total moment of inertia. So first let us start from the rod. I about the rod is equal to 1 by 12 mi square. The moment of inertia for all shapes is given in our class book of class 11 physics book volume 1. It is given as a tabular column. If you refer that, the moment of inertia of all regular shapes is given in that tabular column. So from there we have taken the value as 1 by 12 mi squared. So substituting the value of m and the length L value, we get I rod is equal to 1 by 12 into 3 into 0.8 the whole square. Simplifying, we get the moment of inertia about the rod as 0.16 kilogram meter square. Now the mass of the sphere is 5 kg. The radius of the sphere is 10 centimeter, which is converted into meter. It gives 0.1 meter. The moment of inertia about its center of mass is IC is equal to 2 by 5 mr square. This is once again found from the tabular column. The moment of inertia about the sphere, about the geometric center is given by, we have to use our perpendicular axis theorem. We have I sphere is equal to IC plus MD square, where D is the distance between them, which is 40 centimeter plus 10 centimeter, which is the radius of the sphere. So the center of mass from the center point through which it is rotated is 40 centimeter plus 10 centimeter, which is equal to 50 centimeter. Converting that into meter, you have got 0.5 meter. So the moment of inertia about the sphere is equal to 2 by 5 mr square plus md square. Substituting the m value, r value, d value and simplifying, we get I sphere is equal to 1.27 kilogram meter square. So we need to add all these values to get the total moment of inertia. So total moment of inertia is given by moment of inertia about the rod plus 2 into moment of inertia about the sphere, because both the spheres seems to be of regular shape. So it is 2 into moment of inertia about the sphere. So substituting the values and simplifying, we get the total moment of inertia as 2.7 kilogram meter square. The next problem, a disk of mass 500 gram and radius 10 centimeter can freely rotate about a fixed axis as shown in the figure. Light and inextensible string is wound several turns around it and a 100-gram body is suspended at its free end. Find the acceleration of this mass. So m1 is the mass of the disk whose radius is r. m2 is the mass of the suspended body. So converting all these mass into SI unit, we have m1 as 0.5 kg, m2 as 0.1 kg, r is 0.1 meter. So first we will find the torque. Since this object is attached to a pulley-like structure, you will have the rotational equilibrium. Hence, the torque is given by force into perpendicular distance. Here, force is the tension force. So, T into the perpendicular distance is R. So, this is the torque. So, tau we know that the relation is I alpha. So, I value is m1 k square and alpha is equal to A by R. Using the relation between linear acceleration and angular acceleration, we have substituted for alpha as A by R. So, simplifying this, we have the T value as m1 k squared A by R square. This is the tension force value. This we are going to substitute in our free body equation, which is m2g minus T is equal to m2a. Substituting for T, we have m2g minus m1 k squared A by R squared is equal to m2a. Taking all the A terms on one side and simplifying, we have m2g is equal to m1 k squared by R plus m2 into A. We need to find the value of A. So have A on one side, the remaining terms take it to the denominator. We have m2 divided by m1 k squared by R plus the value of k squared by R is given as 1 by 2. So substituting this value, we have m2 divided by m1 divided by 2 plus m2 into g. So 2m2 plus m1 by m2 into g. Substituting the m1 value, m2 value, g value and simplifying, we have A is equal to 2.857 meter per second square. The next problem, a jester in a circus is standing on with his arms extended on a turntable rotating with the angular velocity omega. He brings his arms closer to his body so that his new moment of inertia is reduced to one-third of the original value. Find his new angular velocity. We know that the torque is equal to constant. So tau is initial will be equal to final. So initial will be I omega is the expression for torque. So initial it is given with the suffix I. Final is given with the suffix F. So I omega is equal to if omega f. Here we need to find the value of final angular velocity omega f. So writing omega f, we have omega f is equal to I omega divided by 1 by 3I. Here the value of if, the final moment of inertia is given as 1 by 3I. So substituting this value and simplifying, we have omega f is equal to 3 times omega. So the final angular velocity is equal to 3 times the original value. The next problem, find the rotational kinetic energy of a ring of mass 9 kg and radius 3 meter rotating with the 240 rotation per minute about an axis passing through the center. You can see the rotation in the animation. RPM is the unit for rotation, which is speed of rotation per minute. So the rotational kinetic energy is given by Ke is equal to half I omega square. I value is mr square for a ring. This is also found from the tabular column. So I is equal to mr square. First let us find this value. So I is equal to m value, r value, substituting and multiplying, you get the value as 81 kilogram meter square. Now we need to find the angular velocity, which is given in the unit of RPM, revolution per minute. So this is for per minute. We know that the rotation or any unit for time should be per second. So from minute to second we have to divide it by 60. This is the rotation for 1 minute. And the total rotation, the angle in the total rotation, here the total rotation is a circle. So the total angle will be 360 degree, which is 2 pi. So when you want to convert this into radian per second, the total angle in a circle is 2 pi and the time is 60. So you have to multiply by 2 pi by 60. Hence you can get the omega value per radian per second. So substituting this value in kinetic energy, which is half, I value is 81 and omega squared is, substituting this value, we have 25,920 kilojoule. This is the value of kinetic energy. The next problem, a rolling wheel has a velocity of its center of mass as 5 meter per second. You can see the rolling wheel in the animation below. If its radius is 1.5 meter and angular velocity is 3 radian per second, check whether is it pure rolling or not. Here the velocity of center of mass is given as 5 meter per second, radius is 1.5, angular velocity is 3 radian per second. The rotational velocity, we know the formula as V rotation is R omega. So V rotation is equal to 1.5 into 3, which is 4.5. So if you see the value 4.5 is less than 5, that is V rotational is less than V translational. Hence it is sliding and not rolling. The next problem, a solid sphere is undergoing pure rolling. What is the ratio of its translational kinetic energy to the rotational kinetic energy? In the near animation, you can see how a sphere is undergoing a rotation motion. So the total kinetic energy is a sum of translational kinetic energy plus rotational kinetic energy. And we know the expression for kinetic energy, which we have derived in the theory equation as half mvm squared plus mvcm squared into k squared plus by r squared. This expression we have seen how the movement is taking place with respect to center of mass and point of contact. This equation already we have derived. So the kinetic energy for the sphere is given by half mv squared cm into 1 plus k squared by r squared. This is the total kinetic energy, which is equal to half mv squared of cm plus half mvcm the whole squared into k squared by r squared. Here we need to find its ratio. So we can cancel the terms which are common. mv squared by r, they are common. So we can cancel them. Hence we have kinetic energy is to translational kinetic energy is to rotational kinetic energy as 1 plus k squared by r squared is to 1 is to k squared by r squared. First term is for kinetic energy, total kinetic energy, that we need not find. We need to find only the ratio between translational and rotational kinetic energy. So skipping the first term, we have kinetic translational is to kinetic rotational is equal to 1 is to k square by r square. For solid sphere, the value of k squared by r squared is once again obtained from the tabular column, which is 2 by 5. So substituting this value, we have kinetic energy translational is to rotational kinetic energy as 5 is to 2. Four round objects, namely a ring, disc, hollow sphere and a solid sphere with the same radius r, starts to roll down on an inclined plane at the same time, which you can see in the following animation. The question is, find out which object will reach the bottom first. We know that all the four objects, the radius of gyration, the relation between k and r is once again obtained from the tabular column as r square root of 1 by 2 r square root of 2 by 3 r square root of 2 by 5 r. So substituting this value 1 by 2 and taking the square root, we have the radius of gyration k value as 1 r, 0.707 r and 0.816 r and 0.632 r respectively. And we know the time taken expression is given by t is equal to square root of 2h into 1 plus k squared by r squared the whole divided by g sine square theta. If you find in this equation, k is in the numerator and also t is in the numerator. So both of them are directly proportional to each other. So as k increases, the time t increases. So t is maximum for the first one, which is the ring. So ring will have the highest k value. Hence it will take a long time to reach the ground. So the ring is not lost in the race. So the first will be solid sphere, the second is the disc, third is the hollow sphere and the last is the ring. Next problem. A uniform disc of mass 100 gram has a diameter of 10 centimeter. Calculate the total energy of the disc when rolling along a horizontal table with a velocity of 20 centimeter per second square. You can see the rolling in the following animation. Mass of the disc is given as 100 gram. When you convert it into kilogram, you have 1 by 10 kg. Velocity of the disc is 20 centimeter per second. So when you convert this into meter per second, you have 0.2 meter per second. The R value is given as 5 centimeter, which is equal to 5 into 10 power minus 2 meter. Omega value you can found using the relation V is equal to R omega. So omega will be equal to V by R. Substituting V value and R value, you have the omega value as 4. So the energy is a sum of translational energy and rotational energy, which is half mv square plus half I omega square. So you can take half as common. So you have half into mv square plus I omega square. Substituting m value, v value, I value and omega value and simplifying, you have half into 1 by 10 into 0.2 into 0.2 plus half into 1 by 10 into 25 into 1 by 4 into 16. So simplifying, we get half into 4 by 1000 plus 2 by 1000, which is equal to half into 6 by 1000, which is equal to 3 into 10 power minus 3 joule. This is the value of the energy. The next problem. A particle of mass 5 units is moving with the uniform speed of v is equal to 3 root 2 units in the xy plane along the line y is equal to x plus 4. Find the magnitude of the angular momentum. Mass is given as 5 units. Speed is given as v is equal to 3 root 2 units. And the value of the line is given as y is equal to x plus 4. So first we have to find the magnitude of angular momentum. Angular momentum is given as L is equal to m into r cross v. So m into r vector. R vector is the position vector which is given in terms of x and y. So how can we write r? We can write r as x I cap plus y j cap into velocity. Since the position vector has the two components x and y, the velocity should also have the two components I and j. So here we have v I cap plus v j cap as the v vector. So multiplying these two, we know that I cross into I cross is equal to 0. So we need to cross I and j. So when you multiply I and j, you have the value as xv. I into j is equal to k. So xv k cap minus the next term will be yj cap into vj cap. J cap cross j cap is equal to 0. So j cap should be multiplied with I cap, that is yj cap into vi cap. J cap into I cap is equal to minus k cap. So here you have minus vy k cap. So multiplying this, you have m into x v k cap minus vy k cap. Now here instead of y, we have to substitute the given equation x plus 4. So substituting that and multiplying, and you get two terms to be cancelled. So the remaining only one term will be L is equal to minus m v k cap. Substituting m value, v value, we have minus 60 root 2 k cap. So L is equal to 60 root 2 units. This is the magnitude of angular momentum. The next problem. A flywheel rotates with a uniform angular acceleration if its angular velocity increases from 20 pi radian per second to 40 pi radian per second in 10 seconds. Find the number of rotation in that period. So initial angular velocity is given as 20 pi radian per second. Final angular velocity is given as 40 pi radian per second and the time is given as 10 seconds. First let us find the angular acceleration, which is alpha, which is omega f minus omega I by t. That is final velocity minus initial velocity divided by time. So 40 pi minus 20 pi, which is equal to 20 pi divided by 10, which is 2 pi radian per second. Here we use our third equation of motion for rotational motion. We have theta is equal to omega naught t plus half alpha t square. Substituting omega naught alpha t value, we have the theta as 300 pi radian. So number of rotation is found by the formula theta divided by the total angle. That is the angle through which it is moving divided by total angle. We know that the total angle in a circle is 360, which can be written as 2 pi. So theta by 2 pi will give you the number of rotation. So theta is found to be 300 pi. The total angle is 2 pi. So cancelling this, we have 150 rotations. The next problem. A uniform rod of mass m and length L makes a constant angle theta with the axis of the rotation which passes through one end of the rod. Find the moment of inertia about its gravity. We know the moment of inertia about the axis which is passing through the CG as I naught is equal to ml square divided by 12. This is once again found from the tabular column. Here if you find the L is the distance between the axis through which it is rotated and the L. And here the distance between them is given as L sine theta. So substituting for L as L sine theta, we have I value as ml square sine square theta divided by 12. So I naught is equal to ml square sine square theta divided by 4. Simplifying, you get this answer. So adding them both, we have ml square sine square theta by 12 plus ml square sine square theta by 4. You have half ml square sine square theta. The next problem, two particles P and Q of mass 1 kg and 3 kg respectively start moving towards each other from rest under mutual attraction. What is the velocity of center of mass? Here it is given that mass of the particle is 1 kg, mass of the other particle is 3 kg. They are mutually moving towards each other, hence they form an internal system. So when they both form a system, no external force is acting on the system. If no external force is acting on the system, the center of mass is found to be at constant. So the velocity of the center of mass will be equal to 0 if no external force is acting and it is moving all about the internal force. Hence the center of mass velocity will be equal to 0. The next one, find the moment of inertia of a hydrogen molecule about an axis passing through its center of mass and perpendicular to the interatomic axis. So given mass of the hydrogen atom is 1.7 into 10 power 27 kg, the interatomic distance is equal to 4 into 10 power minus 10 meter. We need to find the moment of inertia. So the moment of inertia is given by half mr square. So half into this value is once again got from the tabular column. The mass of the hydrogen, the shape of the hydrogen is found to be a sphere. So here we use the mass and the moment of inertia value of a sphere. So here it is half mr square, half into m is 1.7 into 10 power minus 27 into r square. R, if you see the diagram, you can find the r value as 4 into 10 power minus 10 meter. So r square means it will be 16 into 10 power minus 20. So simplifying, you get 1.86 into 10 power minus 46 kilogram meter square. This is the moment of inertia.